Good morning, everyone. My name is Mandulanik Kumar. I am from Department of Electrical and Computer Engineering at Colorado State University. Today, I'll present our work on total ionizing dose effects on lateral charge migration in 3D charge trap NAND memory. In this study, we investigate how gamma radiation influences threshold voltage dynamics, both during irradiation and in the post-irradiation retention phase. Let me briefly outline the structure of this presentation. First, I will discuss the motivation behind studying TID effects in commercial NAND memory. Then I'll provide background on state-of-the-art 3D NAND charge trap and explain the fundamental mechanisms of charge loss and TID effects. After that, I'll describe our experimental setup and measurement methodology. Then we will move to the experimental results, including both during radiation behavior and post-TID retention characteristics. Finally, I will conclude with key findings and implications of this work. Now let us begin with the motivation. Reliable data storage is essential for critical space environments, nuclear plants, avionics system, particle accelerators. In addition, space data centers are emerging as a future concept, further increasing the demand for reliable storage solutions. At the same time, the number of satellites is increasing dramatically. In space, depending on orbit type, devices can experience radiation levels ranging from a few kilorad per year in lower Earth orbit to nearly 1 megarad per year in medium Earth orbit. Projections suggest that more than 100,000 satellites could orbit our Earth in the near future by 2030. This means that commercial off-the-shelf memory chips will increasingly be deployed in radiation environments. 3D NAND is the most advanced and most promising storage solutions available. Given this context, understanding how advanced 3D NAND behaves under radiation becomes critically important. With that motivation, let us review the current status of 3D NAND technology. Flash have evolved through both geometric and logical scaling. Earlier generations relied on planar 2D floating gate structures. However, aggressive scaling introduced reliability challenges such as few electronostatistics, increased noise, strong cell-to-cell interference. To overcome these limitations, the industry transitioned to 3D NAND, increasing the number of stack layers instead of shrinking the lateral dimensions. Today, we have already more than 200 layers, and future devices are expected to exceed 1,000 layers. Now, stacking more and more layers along the Z direction is problematic because of the tapered channel hole shape. Geoscaling, or reducing the spacing between the word lines, solves this issue to some extent. Multiple deck depositions have been adopted by industry to solve the stacking issue further, where a single deck can accommodate 32 to 44 layers. Moreover, CMOS circuitry can now be fabricated on a separate wafer with a different thermal budget in the process and moved below the memory stack by the wafer bonding known as CMOS directly bonded to the array technology. At the same time, logical scaling progressed from SLC to MLC, TLC, and QLC, and even beyond, storing up to 4 or 5 bits per cell. These architectural innovations improve the density quite a bit, but still retain the charge loss mechanisms from its past predecessors. To understand radiation effects, we must first understand how charge is lost in 3D NAND structure. This slide illustrates the structure of a 3D charge trap NAND string. Charge is stored in the silicon nitride layer, surrounded by tunnel oxide and blocking oxide. The silicon nitride layer is shown in red color in the schematic. The silicon nitride region is shared along the cells in a single string. There are two primary charge loss pathways in a 3D charge trap NAND flash memory string. Vertical loss as usual through the tunnel oxide. The shared nature of the nitride region creates a secondary loss mechanism, lateral charge migration, along the lateral nitride layer between the neighboring word lines. Lateral migration is unique to charge trap technology, and it's the quicker charge loss process. This brings us to a closer look at the lateral charge migration. In charge trap 3D NAND, both electrons and holes can migrate laterally along the nitride storage layer. This lateral movement redistributes stored charge between neighboring cells, especially along the vertical string. In fresh unirradiated devices, shallow trap electrons are the primary contributors to this process. Their movement leads to early retention loss, particularly in TLC and QLC chips, where threshold voltage windows are narrow. Understanding how radiation interacts with this mechanism is central to this study. Here, we observe the impact of lateral migration on threshold voltage. LCM leads to short-term charge loss, typically visible as a VT downshift quickly in programmed states. In some neighboring states, redistribution can also produce VT offsheet. For example, here the L7 state is losing more than 100 millivolt within 5 days of retention, while the L1 state, they're actually receiving electrons from the neighboring high programmed states and moving up a little bit. Now the key question becomes, how does total ionizing dose interact with this already complex charge redistribution process? Here I'm showing a simplified planar Venn diagram of a 3D charge trap NAND flash memory cell with its programmed state. The red electrons in the silicon nitride layer are the shallow trapped electrons, and the black electrons are the deep trapped electrons, and the cell is under radiation. Now, under TID, three basic mechanisms can happen. Number one, TID generates electron hole pairs in dielectric layers of tunnel oxide and blocking oxide. Electrons, due to their high mobility, are quickly swept out. Holes, however, are slower and can become trapped in the oxide or the interfaces. Number two, these oxide trapped holes can move slowly in the towards the silicon nitride and can eventually get injected in the nitride. And number three, some of the shallow trapped electrons can receive energy from the gamma ray photons, jump over the barrier, and get lost, which is called thermionic emission. Now, the major charge loss mechanism in a flash memory cell, charge trap flash memory cell under radiation, is oxide ionization or hole deposition in the oxide, and that creates VT shift of the memory cell. Now, the VT shift of the memory cell can be approximated using very simple equations. Assuming typical thicknesses, and the cell is in L7 state, assuming all that, we can get a maximum VT shift per kilorad to be 14 millivolt per kilorad, which gives us a rough idea of what to expect. In charge trap NAND, because the LCM or lateral charge migration, a quicker charge loss process, is already present, so these TID effects can alter both charge retention and migration behavior. With the physical understanding in mind, let me now describe how we experimentally studied these effects. So we use commercial chips for this evaluation, and we interface these chips through our in-house built hardware. And we used commercial 64-layer charge trap TLC 3D NAND chips. The devices were irradiated using a cesium-137 source. Importantly, we accessed raw threshold voltage distributions by bypassing ECC, allowing direct observation of state shifts and distribution widening. We monitored VT distributions across all programmed state from L0 to L7 through irradiation, and here's the VT encoding of the digital states, and here's the experimental flow of our irradiation scheme. We first erased the whole block and they programmed with a randomized data pattern. Then we irradiated the chip or memory array at a fixed dose rate up to 30 kilorad, and we took data at equal intervals, like after every 5 kilorad or 10 kilorad. After the 30 kilorad total dose was done, we kept the memory chip in room temperature and read the data from time to time. Here we show the evolution of threshold voltage distributions during irradiation. So here's the L7 state distribution during irradiation doses. For higher programmed state of L7, we observed a downshift of the distributions with each incremental dose, and the distributions widen with each incremental dose. The data, measured data, is shown here through symbols, and the lines are representative of the Gaussian fits for a clear visual. But for the lowest state L1, we observe a slight upshift and of course distribution broadening. Now this opposite behavior of L1 indicates a very strong state dependency in the TID response. However, this behavior is more interesting when you examine the VT shifts of all programmed states. So here is the median VT shifts of all programmed states from L1 to L7, and we observe two interesting things. Now, first one is the state dependency. There is a strong state dependency in the TID response of the VT levels from L1 to L7, and it is spread out up to the highest shift of 8.8 millivolt. And in all of the states, in the higher states, like from L4 to L7, we see that at some point between 10 kilorad and 15 kilorad, the slope of the VT loss changes. And when we analyze the VT shift slope versus dose, we see two distinct regions. Let's examine the characteristic of L7 VT loss. Below approximately 10 kilorad, the slope is steep, around 35 millivolt per kilorad. and about above 10 kilorad, the slope reduces to about 18 millivolt per kilorad. Interestingly, all of both slopes and the total shift exceeds the oxide ionization model that we discussed. This suggests multiple concurrent mechanisms beyond the simple hole trapping is happening. To explain this, we examined the shallow trap electron dynamics more closely. It's a three-dimensional Venn diagram of an L7 state cell during irradiation. So as usual, number one, hole deposition happens in the oxide. And number 2 and 3, the shallow electrons, the red electrons here are the shallow electrons. The shallow electrons, they receive energy from the gamma ray photons, and they can jump over the barrier in photoemission, and the LCM can be enhanced because the shallow electrons are already very mobile, but receiving energy from the gamma ray photons make them more energetic, and enhanced LCM can happen. And after 10 kilorad, what happens is most of the shallow electrons, they have been depleted by the earlier doses. So the remaining shallow electrons, they either get stuck because of the increased amount of oxide holes in the oxide, and they can also experience vertical charge redistribution towards these holes, which contributes to negligible amount of VT shift at the end. We refer to this as VCR. So below 10 kilorad, LCM is enhanced by gamma ray photons, and most shallow electrons are depleted. And after 10 kilorad, the remaining shallow electrons experience basically VCR, or vertical charge redistributions. This transition explains the observed change in slope of the VT shift characteristic of L7 and in other states, and indicate that the shallow electron depletion may be the root cause of the large initial shift and the beyond theoretical limit of oxide ionization caused VT shift. Now let's examine what happens after the irradiation stops. Here I first show the retention behavior of all programmed states again from the charge trap array of the unirradiated memory array. And the LCM signature of LCM is present in all of the states. The L7 state losing very fast the large amount of VT, and the L1 state is moving up a little bit very quickly. This is a classic signature of LCM. But surprisingly, after irradiation, in the irradiated array, lateral charge migration becomes negligible because the VT levels are surprisingly stable over 3 months of room temperature retention. In other words, the usual short-term LCM-driven retention loss is suppressed. This leads to what we call anomalous post-TID retention behavior, where LCM has a negligible impact of the irradiated stored data. To understand why this happens, we investigated the role of oxide trapped holes again. In unirradiated memory, the shallow trapped electrons dominate the lateral charge migration, as already discussed. Now during radiation, what happens is most of the shallow electrons are depleted because of the radiation dose, as discussed earlier. So after irradiation, a few shallow electrons remain, and the oxide trapped holes partially immobilize or redistribute these shallow electrons. As a result, fewer mobile electrons remain available for further lateral migration. So post-TID retention is then governed mainly by deeper traps and vertical redistribution rather than lateral migration, and gives this very stable behavior after irradiation. And all of this fundamentally alters the retention dynamics of the device. With that, let me conclude. Let me summarize the key findings. First, TID-induced oxide holes deplete or immobilize the shallow electrons in the 3D charge trap NAND, which produces a large initial VT shift that exceeds the classical oxide ionization limits. Second, TID introduces anomalous post-TID retention behavior by suppressing lateral charge migration. Finally, after irradiation, retention becomes dominated by deeper traps and vertical charge distribution mechanisms. These findings provide more important insight into radiation reliability of advanced commercial 3D charge trap memory. Thank you for your attention.